In this video, I am going to help you read Riemann sum notation. All right, so we just did an example with the specific function square root of x, but what if we had a different function, or any function in general? What are we doing? You've got some function of x. There's nothing special about quadrant 1, but it just helps us visualize, especially in the beginning. You've got some interval in the domain, and the game is we want to find the area under that curve over that domain, and really meaning the area between that curve and the x-axis, right? So this is what we're trying to calculate, is this area. And what you do is you chop up this interval into n subintervals. And in the text, we like to give these, because I don't want to specifically just say 4 intervals. I want to work with n. So I'm going to have a be just x sub 0 or x naught. Then the next place where we've got a partition in the domain, we've got x1, x2, x3, continuing on and on, x4, x5, blah, 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 and then finally at the very end have xn. Right, so here's xn. And because I'm doing right endpoints, and again, that n right there is the number of rectangles that we're going to have, n partitions of that domain. What are you doing? You're adding up areas of rectangles. Areas of rectangles are heights times bases. So if I'm using my right endpoint between a, or x naught, and x1, I'm going to use x1, f of x1, that's the height of the rectangle that I want. I'm going to choose that height, not this height. So there's this area. All right. So f of x1 times, and then the base, all the bases here are always little tiny changes in x. Plus, for the height of the next rectangle, that'll be f of x2. Between x1 and x2, I'm going to choose x2, the right one, and then f of x2, that's the height, that's the y value of my next rectangle. Right, so height times your base. And I've got so much space. How about I put the picture up above? Right? And then for my next rectangle, the height's going to be f of x3 times my base. We'll change an x. This height. And so on and so on. And then finally at the end, for my nth rectangle, between x sub n minus 1 and x sub n, I'm going to choose x sub n. Let's see if I can fit that in there. Right. So between those two, I'm going to choose b. I'm going to choose x sub n. And that's going to be the height of my very last rectangle, my nth rectangle. So plus dot, 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 plus the last height is f of x sub n times a little change in x. That's my pink height written right there. You can write this more concisely with summation notation. What are you adding up? You are adding up these heights times your little bases. I'm going to use I for my index, and where am I starting? I'm starting at I being 1, and I'm ending at I being n. Start at I equal 1 and end at n. All right. We also can use left endpoints, and I want us to actually talk about this notation. Here we're looking at a more rigorous notation. And we need this. Why? Because we're going to want there to be not just n rectangles. I want there to be infinitely many rectangles. So I'm going to want to take a limit as n goes to infinity. I need to be a little tighter with my notation and language. Let's look at the left endpoints. All right, again, we're going from A to B. You're going to partition up that interval into n subintervals. So I'll have n rectangles. A is x sub 0, then we got x sub 1, x sub 2, x sub 3, etc. And then we have at the end x sub n minus 1. And what's B? In fact, I think I like this a little bit better. And at the end, we have x sub n, right? And between x sub 0 and x sub 1, I'm going to choose x sub 0. So f of x sub 0 is going to be the height of my first rectangle. And then between x sub 1 and x sub 2, I'm going to choose x sub 2. Between x sub 1 and x sub 2, I'm going to choose x sub 1. That's going to be the height of my second rectangle. Between x sub 2 and x sub 3, I'm going to choose x sub 2. F of x sub 2 is the height of my third rectangle, and so on, right? So these are the areas that I would be calculating. Look at how those are overestimations right there, because my function is decreasing on that interval. At the end, between x sub n minus 1 and x sub n, I'm going to choose x sub n minus 1. So f of x sub n minus 1 will be the height of my last rectangle, my nth rectangle. All right, so this is what it looks like. I'm going to do L for left endpoints. N, I've got n rectangles. What am I adding it up? I'm adding up a height times a base, right? I'm adding up a bunch of areas of rectangles. And this first height is f of x sub 0, the orange height. Plus the yellow height, f of x sub 1, times your little change in x. Plus the height of my, the green height there, f of x sub 2, times your little change in x. Plus, keep going and going and going in this fashion, and then at the end, the area of my nth rectangle, well, its height is the blue height there, which is f of x sub n minus 1, times your little change in x for the base. All right, we can write this a little bit more succinctly with summation notation. What are we adding up? We're adding up heights times bases. I'm going to use I for the index. I'm starting at I being 0, and I'm ending at I being n minus 1, right? Starting at I equals 0 and ending at I being n minus 1. All right, so it's a little bit more concise. These are the things that we want to take limits of as n goes to infinity.